Alright, so in our second lesson in this mini module about the basic model of forces represented as vectors and the various vectored operations that we're going to be pursuing, note that we're going to take a look at resultants of forces. We'll look at position vectors, unit vectors, all of which you may have already had in other contexts, maybe even forces, but this is all within this sort of world where we've got an applied force down here and it's at some particular location, some sort of angle. How do we handle it in various ways? Last time we talked about the polar coordinate system version of this, the rectangular coordinate system, which is also sometimes called the component system with I and J bases or the components there, and then a true graphical, which would be draw to scale kind of approach. Right, so the particular instance we're going to take a look at here is that we've got this little bracket that's fixed to a wall, three different forces that are imposed. I'm going to call them left to right, F1, F2, and F3, and the first thing we're asked to do is express these forces in vector form. That's a particularly simple thing to do here because the forces are aligned with the global coordinate system, so their description becomes so much easier here. F1 is directly in the y-axis, and so it's got 40 pounds J, but it is going downwards, so that's negative in our coordinate system. So minus 40 pounds J. Second force is acting entirely upwards, so we don't have to find any x and y components because it's easy. The y component is entirely 60 pounds. It's going upwards, same direction as J, so positive. And then the last one, F3, this one's entirely horizontal, so that's 50 pounds I, but it's in the opposite direction of the positive, so it's a negative 50 pounds. That's all there is to it in that particular one. That's just a sort of a quick little review here. The position vectors are useful when we start trying to answer questions about, well, how much do each of these individual forces cause this bracket to want to try to rotate around point zero, what we call the moment of the force. And we'll be dealing with that soon, but not in this lesson. So that's what the position vectors are really for. So position vectors have to go from one place to another. In this case, we're told position vectors of each force from the origin to the respective point of application. So for this first one, then it would start at O and go out to this position. We'll call that R1. And it's pretty straightforward. It's just taking the coordinates of each of these points and then subtracting off to get the deltas, and especially easy in this case because we just have a positive 10 inches I for R1. R2 would go out to the point of application of the second force, and so that will be 20 inches I. And then R3 is the only one that turns out to have any, well, it's still trivial, but it's at least different. And there's your R3. It's got X and Y, so we have a total of 25 inches in the I, and we have plus 10 inches in the J. Again, these are going to be useful at some point for doing some other kinds of calculations that have to do with the effect of the rotational effect of a force. Right? Then in part C, we're asked to find the unit vector from the origin to the point of application of the 50-pound force. Other kinds of things that happen in our statics world, in the vector mechanics world, include doing triple mixed products. So that's dot and cross products, and the unit vector is going to be very helpful. When we're doing three-dimensional work, they become somewhat crucial. This is really two-dimensional x and y only. Right, so let's look at this unit vector that's along this same direction as 3. That's U3. Okay, so that's the unit vector with same orientation or direction as R3. Its length is equal to 1. That's what the unit part means. Right? And the way that we do that is we just take, since we already have R3, and divide R3 by its magnitude. right? And we find the magnitude with essentially the Pythagorean theorem. R3 is equal to the square root of the sum of the squares of each of the components. That would be true in 3D as well. So that'd be Rx squared plus Ry squared. If we had a Z, we'll put it in here. We don't here, right? That's how that would work in 3D. Really simple. And so let's just get rid of that because that's 0 in this case. And we come along then and square root of 25 squared plus 10 squared. That'll be the square root of 725, right? 625 plus 100. And that is 26.92. Notice it's actually 26.9258, and the way when you round things, and I decide for arbitrary reasons to keep it to 4 digits, that if it's an even number, the scientific method, an approach to this says you always end up with an even number when you have a 5 sitting here. It doesn't matter what any of these other numbers are, right? So that would always go to the 2, and that's how you sometimes go down, sometimes go up in that particular case. A lot of people are very sloppy about that, and probably only matters in very careful scientific work, but nonetheless it's a holdover for me. So that's 26.92 inches, and then what we do is we take each one of those components and we divide by that, because that's now a scalar quantity. So this is 25 over 26.92 I plus 10 over 26.92 J. And so if we want to have that in decimal form, then that would become 0.928 I plus 10 divided by 26.9, nuts. I took that out of memory. 10 divided by 725 radical, and that's 0.371. Now, remember, the length is not just adding those two up, right? Those, you have to take the square root of the sum of the squares, and when we do that, I have a little rounding error probably in here. Take the square root of that, and we get something close to 1. Again, there's a little bit of rounding errors because I got rid of the digits past the 8 on that one. So that just demonstrates that that really does have length of 1. Again, square root of the sum of the squares to get that particular length. And that's how we deal with position vectors, unit vectors, and so on and so forth.